Welcome calculus fans, a video today on vector calculus and motion in space. So briefly talk about a few things. We'll talk about obtaining velocity and acceleration from a position vector. We'll talk about applying Newton's second law to find a position vector, and then we'll talk about similarly applying Newton's second law to projectile motion. The good news here is that these are things we've all done before. Just now we're doing them with vector valued functions rather than scalar valued functions. Okay, I'll remind you that when you have the position of some particle given by r of t, then the velocity is the first derivative of position and acceleration is the derivative of the velocity or the second derivative of the position. As we saw previously, the derivative of a vector valued function can be written in terms of this limit definition, but all of our rules from calculus 1 and 2 carry forward here about product rules and quotient rules and so on and so forth. So here's an example. Let's find the velocity, acceleration, and speed of a particle with position given by this vector t I hat plus t squared j hat plus 2 k hat, and we'll do this at t equals 1. So here are those velocity and acceleration vectors, the velocity vector I hat plus 2t j hat, and the acceleration vector 2j hat. Now, if we want to know the velocity and acceleration at a particular moment in time, just plug in that moment in time. So here are those velocity and acceleration vectors at t equals 1. And if we want to know the speed, of course, the speed is just the magnitude of the velocity. So in this case, the speed at t equals 1 is the square root of 5. Okay, move on and talk about Newton's second law. I'll remind you that Newton's second law of motion tells us that the mass times the acceleration of an object is equal to the sum of the forces acting on the object. So oftentimes this Newton's second law of motion is represented by the equation ma vector equals sum of f sub I vectors. Possible forces might be like the force due to the acceleration of gravity, minus mg in the k direction, or external forces like springs or damping forces or things like that. Many of you are in this class because you're eventually going to take Math 347, and these type of forces end up being important in Math 347. So you'll circle back to that for sure. Okay, here's an example of the application of Newton's second law. Let's find the force acting on an object with mass m moving about a circular path with constant angular speed given by omega. Okay, one consideration here that I forgot to mention is that we're going to assume the circle has a radius of a. Then the position function is given by the position vector valued function is given by r vector of t is a cosine omega t I hat plus a sine omega t j hat. From that position function, we can quickly compute the velocity and the acceleration functions. So just using the chain rule, a couple of times we see that the force here, the acceleration rather, is given by minus a omega squared cosine omega t I hat minus a omega squared sine omega t j hat. And of course the force is given by the mass times acceleration. So the mass times the acceleration is just m times that a vector. It turns out that the force is a constant multiple of the position, which is a perfect, in this case, example of what's called centripetal force. Sort of a cool deal. Okay, last thing we'll talk about in this section is projectile motion. So using Newton's second law, we can find expressions for the velocity and position functions just by integrating these vector valued functions. Here's an example of that. Let's suppose that a projectile is fired with an angle of elevation alpha and an initial velocity v naught. We'll assume air resistance is negligible and that the only force is due to the acceleration of gravity. Here we'll find the position function. So again, we'll apply the second law of motion. Says that mass times acceleration is the sum of the forces. In this case, the only force to consider is the force due to the acceleration of gravity. This gives us an equation for the acceleration. So here's that equation for the acceleration. The acceleration is just minus g in the k direction, so k hat. Now from that we can go ahead and find expressions for the velocity and the position. So here are those two integrals. The velocity vector is given by the integral of the acceleration vector. We'll express that as minus gt k hat plus some constant vector, I'll call that c1. Of course, given that the velocity at 0 is v naught, we can take c1 vector to be v naught, giving us a perfectly good expression for the velocity. Similarly, the position vector is given by the integral of the velocity vector, which we'll express as minus 1/2 gt k hat plus v naught t plus c2. When t equals 0, we're taking our position to be at 0, which tells us that the constant vector c2 is the 0 vector. This, as it turns out, gives us a perfectly good expression for the position vector, written here as minus 1/2 gt squared k hat plus v naught t. Now we can use those vectors to identify the motion in terms of this initial angle of elevation alpha. So given our initial velocity vector, whose magnitude I'll take to be the scalar v naught, we can see that the vector v naught can be expressed as v naught cosine alpha I hat plus v naught sine alpha j hat. So using that expression for v naught, again here, vector v naught is v naught cosine alpha I hat plus v naught sine alpha j hat. We can substitute into these expressions and derive these two expressions for the velocity vector and the position vector. So those expressions are: the velocity is v naught cosine alpha I hat plus the quantity negative gt plus v naught sine alpha j hat, and the position vector is v naught t cosine alpha I hat plus the quantity minus 1/2 gt squared plus v naught t sine alpha j hat. Okay, hope you've enjoyed this video on motion and vector valued functions. Have a great day, and we'll see you next time. Bye-bye.